Now we come to mathematics, right? So may I start by giving us a short introduction both to the subject and to our two speakers. The Shaw Prize in Mathematical Sciences for 2015 was awarded to Professor Gerd Faltings and Professor Henryk Iwaniec for their contributions to number theory. Number theory is a surprisingly elegant and deep branch of mathematics, treasured for its beauty. Sometimes the public is too much concerned about what use it may have. In fact, when we held a press conference in June announcing the laureates, I was actually tempted to say that it has military applications in China. That would have made the press sit up. I refer to the Chinese remainder theorem, which to us is known as the 韩信点并问题, 韩信点并问题. It goes like this. I was talking to Professor Faltings just now, and he doesn't know the historical context, so I have to tell the story. So there was this General Han about 2,000 years ago. He was trying to count his soldiers. So he made them line up 3 in a row, and he found there was 1 left over. And then he made them line up 5 in a row, and still 1 left over. And then he made them line up 7 in a row, again 1 left over. So how many soldiers did he have? And that's called the Chinese remainder theorem. And it has to do with primes because if it had not been 3, 5, 7, but 2, 4, 6, there may not be a solution. Anyway, so that's the Chinese military application, right? 韩信点并. Number theory has come a long way since then, and some of the most important recent advances are due to the 2 Shaw Laureates here with us today. Professor Gerd Faltings was born and educated in Germany, and now holds a leading position in the Max Planck Institute for Mathematics in Bonn. The Max Planck Institute is sort of like the National Academy in Germany. It is difficult for me to explain in a simple way his very important contributions. Perhaps I can just say that these contributions include major advances in Diophantine equation. You see the word Diophantine somewhere there. And that is asking whether polynomials, certain polynomials have or have not integer or rational solutions. And I shall also, in the same breath, also introduce Professor Henryk Iwaniec. Professor Iwaniec was born and educated in Poland and now works at Rutgers University in New Jersey. I can try to explain one of his most important results, and that is among all numbers of the form of a square plus a 4th power, x squared plus y 4th. For those of you with good eyesight, you can see that somewhere on the board. Among such numbers, there are infinitely many primes. And this theorem is significant because this class of such numbers is very sparse, very rare. And I hope they will also tell us not only about those results, perhaps, but more so about how they find joy in pursuing these questions. So could I first invite Professor Faltings to come to the stage and speak to us.
Okay, thank you very much for the history lesson. I don't have prepared pictures, but anyway, most information will be verbal. So I try to explain things. So in mathematics, well, the difficulty is that, people are aware that mathematics has something to do with calculating, but this was maybe 200 years ago, and since then people have developed important concepts, and modern mathematics is more about concepts than about calculating. So Diophantine equations are equations dealing with integers. Diophantus was a Greek mathematician, and people don't know when he lived. I think the estimates vary by something like 500 years. Diophantine problems are easy to state to the general public because you just say, for example, you look at Fermat's problem, you want to look whether 2 nth powers can be the sum of 2 nth powers can be equal to the 3rd nth power. But on the other hand, if a problem is simple to state, this doesn't mean that it's simple to solve. And in fact, for the Fermat problem, it took all of modern technology to solve it finally in 1994. So what do I mean by technology? So there are mathematical theory and concepts. For example, concepts are the concept of a topological space. So we have things lying around here, and so we want to see how they differ in shape, and we want to have a precise meaning of that. And this is what's today called topology. So we look at things and we allow them to deform them continuously. And for example, we can show that any closed surface, so it doesn't have any holes, is equivalent to a sphere with a number of handles. So we have a sphere, which is just a ball, and we can add one handle, and because we allow this to deform continuously, this is the same as a torus, so like a tire of your bicycle. And then there are spheres with two handles. Well, so this is one. So this is what took some people some time to find out, and also this was done in the middle of the 19th century, and also if one looks at the pioneers, one realizes that you cannot think about anything if you don't have a name for it. So I'm not really in linguistics, but it's clear that sort of they talk about so and so many times connected object and so, but because they have no good terminology, it's difficult for them. So this was one concept, and for me, for the Dirac-Pentane equation, the most important concepts were the so-called algebraic geometry. So algebra usually you think you calculate, so you add numbers. And geometry, you think about objects in space, like triangles and so. And algebraic geometry, you look at such objects which are given by polynomial equations, and you study them using those polynomials. So the advantage of the theory is that you can introduce ideas from geometry to algebra. So one object in geometry, as I said, for example, if you have a closed surface, it's a sphere with a number of handles. And then, for example, in principle, because you're allowed to deform continuously, you could ask maybe there's some clever way I can deform a sphere with two handles into a sphere with three handles. But this, but to show that this is not possible, you develop the so-called invariance, something called homology or fundamental groups, and the homology is a vector space. I'm sorry about this. I have to use this associated to such an object, and the dimension of the vector space for a sphere with G handles is 2G, and because 2Gs are different, if 2Gs are different, then also their doubles are different, and so you see that they cannot be deformed. An important, this you can do for topological spaces, but it was important also to do this for algebraic varieties. And for algebraic varieties, it was especially important because you consider them not only over the real numbers, where we usually think about spaces, but over our so-called finite fields, where they are, you can think that they behave similar to real numbers, but you need some precise theory. And this precise theory was developed in the middle of the last century, around 1960 to 70, by Alexander Grothendieck, who was a French mathematician. He had a very interesting life. I don't want to delve into this because I have only limited time. And he also was an interesting character, and he developed the so-called étale topology. And with this one could introduce those invariants. So what I want to say is that, to do things in modern mathematics, you have to learn some theories. And one could say that, a theory is like a subroutine in programming. This means a subroutine is a program which does something for you, and it has the advantage that you don't have to know about the details. well, you want to do something and you use it. On the other hand, well, if you really want to cut time, well, you can get faster by programming all the details in assembler or something like this, but then you would spend all your time on these details and couldn't think about the important thing. So in this sense, you need the theories to make progress. And in fact, well, in the proof of the Fermat theorem, there were many such theories involved, and so people liked it because it showed that these theories are useful, but some people don't like it. I always get letters which claim that Weil's proof is much too complicated and one has to rediscover the original proof of Fermat. Which I guess, well, my personal opinion is that Fermat didn't have a proof, because otherwise it would have been found. Yes, one should also make the remark that, well, to do something new, you need some tool which wasn't available to other people, because our predecessors were not less intelligent than we are. I guess human evolution doesn't work so fast, so we need something like these new theories. So this maybe is a general fact. Then maybe I should say something about my career. So I studied mathematics in Münster, which is a town in Germany. Well, and I met a nice teacher, Professor Nastold. Well, one thing, he told me that you have to study algebraic geometry, which I did. And I also, well, and his specialty was commutative algebra, which has some relation to algebraic geometry, but wasn't considered rather backward at the time. But I profited from getting a good footing in this theory, and so I graduated in '78. Well, I got a diploma, and then I wanted to go to the US, and I wanted to get a stipend, and with a diploma, the deadline for stipends was already too late, but if you had a PhD, it was easier to get, and so I wrote a fast PhD, and in fact, my PhD thesis was not as good as my diploma thesis. So, but I'm still think that it's better to get a fast PhD than to get good grades. And so I went to the US in '78. I spent 1 year at Harvard University. So first of all, I really learned English. I should say in school I wasn't very good at languages because, I'm not good at remembering things which I don't use. And so if you don't speak English, then I forget about it. And on the other hand, I sort of made many new friends there, which, for example, I met Andrew Wiles, who was a young star at Harvard at the time. And so I spent 1 year there, and I went back to Münster, and I became an assistant to Professor Nastold. And there I made the so-called habilitation, which is an advanced degree, and this meant I could apply for jobs. And there was one job at Wuppertal. I wouldn't dare to apply, but somebody from Münster was on the committee, and he didn't promise me the job, but he suggested that I apply. And so I did. I said, well, maybe it's probably improbable that I get the job, but it won't cost me anything. And so I applied, and I was happy to get the job. So suddenly I was a professor, and I should say I was very happy about this, because I guess most scientists at an early stage, they worry whether they can make a living from the science. I mean, I always was a good student, but I knew that being a good student is different from doing good research. And I think, as a student, you learn about the science, but starting with research, you also have to learn how to do new research, and that's a different topic, and it takes some time. So I got this job at Wuppertal, And I was maybe not overwhelmed is the wrong word, but I was lucky. I proved the so-called Model conjecture soon afterwards. So the Model conjecture was an old conjecture which had been made by Model in 1922, and there had been some progress in the 60s. And Professor Nastold had a friend in Paris, Professor Spiro, who had some ideas how to extend this, to make this work even for number fields. But it was clear that the ideas were not sufficient. There was something missing. But I thought I'll think about it. Even if I don't prove the Model conjecture, something interesting will come out. And as a young researcher, anyway, you need some good topic. And so first of all, I proved something about Arakelov theory, which was a tool used there, and I think it's my first really good paper. And then, I looked at this Model conjecture, and then I found out, I guess I was lucky, that you could replace some arguments which didn't work in my case with a so-called theory of B-divisible groups. And so this way I proved the conjecture and everything else, and I suddenly became a star. And so, but then I had to go on. I mean, different from my predecessor, I couldn't retire after this highlight. And so I looked. There was two developments from the proof of the Model conjecture, where I just got my way through by some tricks, and but I saw that you could do a better job, sort of, to polish everything, that it looks much nicer. And so I went on working on this, and it got me some time. So in general, I should say, after proving such a big theorem, I guess everybody's anxious what to do next, because if you have reached one big mountain, this doesn't mean that the other big mountains are any easier, and you cannot expect to sort of continue like this. But my experience is that, you usually find something useful to do, and if you find something useful and complete it, then you are satisfied with your life, even if it doesn't give you so much recognition. And so so one thing with this conjecture, I sort of got maybe famous in Germany. This meant that I first appeared in newspapers, which was unusual. I wasn't used to it, and I was sort of didn't really like the idea that somebody worried about my hobbies. But I've learned that you have to allow for some publicity, as you could see in the videos during the ceremony. But then I decided that I got offers from the all leading US universities, and so I decided this was my chance to go to the US. So I just got also married at the time, and I thought, if you have no children, or if the children are young, you can just go abroad, and this is a good time. And because I already had been to the US, I knew what to get into, and so I got a job at Princeton, and there I got my two daughters, which are sitting somewhere here. You could see them in the video, I think. And I had a happy time at Princeton, and I should also say I had some success at Princeton. At the end, I wrote my second best paper on Diophantine geometry, on Diophantine approximation. This was sort of, it's like the Boy Scout that you should do a good deed. There was Paul Reuter, who had new ideas to give a different proof of Model, and everybody talked about it and said how great this was, but nobody seemed to be willing to say that it was correct. And so I thought, well, I should look at it and check it. And I not only found that it was correct, but also that one could generalize things. And so I wrote my second best paper. So following the Boy Scouts motto is a good idea. Well, after this, of course, I tried to go on with my theory, and I profited very much from Princeton. So for example, I had lectures by Ed Witten on mathematical physics, and my main conclusion was that physics is not mathematics, in the sense that for him certain things were obvious. This was supposed to be the energy, and so on. And then you have to do a path integral, which is, for a mathematician, is an undefined object, and you manipulate it and you get something. And so I decided, well, that I can't understand it. I sort of can maybe extract some mathematics from his insight by trying to translate them, but I have no chance of rebuilding physics along my line. So this way I spent time at Princeton, and then my daughters became older, and I heard about others who had, expatriates who had daughters, that if you bring them up, if they become too old, then you refuse to speak your language. They only want to speak English, and you have American daughters. So I decided that it's time to go back, and in between I had gotten the Fields Medal, so it was no problem when I indicated that I had interest in going back to Germany to get an offer from the Max Planck Institute in Bonn. I knew its director anyway, and so in 1994 I moved to Bonn, and I had interesting experience with different school systems, of course, but maybe I don't detail this. And so I'm in Bonn, and I should say I've continued to do research, not on the level of the Model conjecture, but I've always found something interesting to do, and I sort of have been satisfied with what I could do. So I think as a scientist, you are sort of privileged that you sometimes at the end of the day, you can show to something and say, I did this. Well, I guess that's basically my life, and nothing interesting has happened.
Now, may I invite Professor Iwaniec to share with us your ideas and work? Professor Iwaniec, please.
Well, let me reverse my presentation by comparison to Gerd. Let me say something first about myself, about how I became a mathematician, and perhaps why I became a mathematician, and then I come back to mathematics to entertain you a little bit with some perplexing problems in number theory. So I was born in Elbląg, industrial city in north central part of Poland, and I think I can say I was fortunate to grow up with my twin brother, who was 8 hours younger. And we were growing together for quite a while until we entered
Thank you very much,
university in
Professor
1966. There was no really, tradition, academic tradition in the family. Nevertheless, my parents really were stimulating and by encouragement and by great attention to knowledge, and that was sufficient for us to get interested in science rather early. Not really in mathematics at that time, and so there's no particular incentive to do mathematics in our elementary school. We entered a technical high school in the town, which specialized in, so we learned quite a big deal of machines and technology, particularly about steam turbines for power plants. That was quite an experience which I think had some effect, trace on my attitudes toward mathematics. For example, mathematicians see the beauty in the mathematical statements, but for me it is not enough. You really can see more deeply, intrinsic beauty after you really establish results. So they can see how you got it, the tools, the machinery used is part of the beauty. It's not just a realization of your goal. Anyway, the atmosphere in the high school was fantastic. I mean, there was no competition. Nobody was really claiming to be number one. Some people were good in one field, the other in the other field of interest. How we got interested in mathematics? Well, because of mathematical contests. First in mathematical circle in Gdańsk, and then in mathematical Olympiads, we were successful. So it boosts your ambition. Our teacher couldn't really do much for us, but he distinguished us in the class by excusing us to take tests. So that's also encouraging, something like that. But having a brother, twin brother, it was a wonderful thing to stimulate each other. We could ask questions themselves and look for answers together. By the way, never competing, by the way. We are really never competing. And so we went to university, the mathematics department, Warsaw University. But also interesting part of it is that by the regulations of the government, we would not be eligible to enter Warsaw because of we lived far away from Warsaw. So winning the Olympiads gave us this privilege of choosing where to study, also without taking entrance exams, which was a great blessing because I don't think I would pass the mandatory exam in Russian language. Right. Anyway, and when we entered university, we decided to work in mathematics in a different fields because we wanted to be intellectually independent, which is, in my opinion, extremely natural. When you grow up together as a twin brother, at some point you would like to split. But of course, we exchange our experiences for all the time, and never, ever competed. Right. And I think my brother is as happy as I am getting the Shaw Prize. Right, so at the university, I was fortunate that I received attention of Professor Andrzej Schinzel from the academy very early, already at the end of the first undergraduate year, and so I specialized very early. Just makes story short, to say that I already had two papers accepted for publication before I graduated. So I never really wrote a PhD thesis in a way, because one of these was accepted, actually, I could get my degree before I got a master's degree, but there is a slight delay because there was a requirement that I have to pass Marxist philosophy, which delayed my defense for 6 months. So I mastered that philosophy in 6 months. Right. Anyway, other interesting episode I would like to mention from that period is the teachers, professors realized that there are a group of good students that would be better if they set a special program for the students, because the regular programs were really too easy. So they created a special group, something like a dozen out of 300 admitted at the time. So we followed from the very beginning a special program. It's an excellent idea. Right? Also, we were really regular guys. We didn't want to be something special. So, but a few of us had an idea of taking exams in advance and pass 1 year and be ahead of our colleagues. But in Poland, and the system so rigid, this very courageous idea required approval from the dean. But the dean didn't object, but he gave us a wonderful lesson. He said that we are foolish because we are going voluntarily to cut off some of the best years in your life, that is the college years. So we listened to him and we finished on time. Right, yeah. And I say this story sometimes to my students because I think there is no need to be fast or and forget the normal life. We had lots of interesting other things to do, hobbies, and actually it gave me a lot of time to do my beloved subject, number theory, which was not a part of the syllabus. And also I started dating a girl, my wife, and etc. So I think there is no rush for such things, right? Right. And etc. Lots of things from my life could be said maybe another occasion. So let me a little bit say about mathematics. I don't really have time to tell what I'm really doing in number theory. So I have chosen for this presentation something a little bit to entertain, and maybe, but also very perplexing subject that is about ineffectiveness in mathematics. I mean, mathematics is considered as very, very precise science, and it's true. But it doesn't mean that there are no controversy. I'm not talking about something proves we are incomplete. I'm talking about precise arguments which are still controversial. I mean, every statement and hypothesis requires rigorous proofs, as we know. Yet there are some results that are hard to accept, even the rigorous proofs. I have in mind the Banach-Tarski paradox, for example. You can subdivide, a ball, let's say gold ball, into two equal balls. So if it's from gold, then it can improve the budget of the government by doing this. The problem is this paradox. It's ineffective construction using, certain arguments that mathematicians are arguing whether they are accepted or not valid. And in number theory, I jump instantly to this, we have some beautiful examples of ineffective results. And sometimes we would like to accept this as a valid argument, or sometimes not. Yeah. And oops. The best to start would be probably the issue of exceptional character, which we consider as a ghost in the number theory house. It's hard to say for general audience here what it is, but maybe I leave some impression. So it's a character. It's a function chi of n which takes values plus minus 1 according to certain rule, depending on this quadratic residue symbol d over n. And the point is that we don't know exactly, or precisely enough to control the distribution of these values. And there is another function absolutely fundamental for the distribution of prime numbers that's called the Möbius function. And since our knowledge is not perfect, we can see by experiments that for certain discriminants the character mimics or pretends to be the Möbius function. And if it is the reality, if it's not only just a foolish expectation, then there will be a lot of progress in the theory of prime numbers and the Riemann hypothesis, including also for that, if that such pretentious character does exist. So, without explaining what it is, let me just give you some logic behind it. I mean, there are statements in number theory which are proved in 2 steps. One step is assuming that such exceptional character exists, and other statement, the other part is under the assumption that such exceptional character does not exist. So combining both, you have unconditional statement. Unfortunately, there's intrinsic problem here. The result is ineffective, because you don't know which case is the case. And so when you have some implied constants that you would like to make numerical computations, it's impossible. And in some circumstances, such results are really grotesque. I mean, just you see, nothing has been established. But sometimes it does, and not enough time to tell when, but this is something really entertaining and also serious in number theory. I mean, sometimes we wish that this ghost, the exceptional character, does exist, because the consequences for the theory of prime numbers, my beloved subject, actually, right, are enormous. You can prove things that are not even capable, that even the Riemann hypothesis is not capable to handle. In spite of the fact that the existence of such character would violate the validity of the Riemann hypothesis, everybody believes in, we do not want to reject, we hesitate to reject the existence of such character because of these consequences. So, and many of these consequences are also related to the distribution of prime numbers. Other great progress that I would like to mention is in sieve methods. Together with John Friedlander from Toronto, we made some substantial enhancement of the theory of sieve. Sieve was his old stuff, created more than 100 years ago with the expectation of proving Goldbach conjecture or twin prime conjecture, but this goal was later recognized that not possible to achieve by this fundamental within the fundamental axioms of sieve method. This was somehow prime numbers were blocked by sort of parity barrier. So we introduced new devices which removed that barrier and opened the door to prime numbers. and got many things about prime numbers. Examples are here, like that prime numbers of m squared plus n to the power 4, I already mentioned before, infinitely many of them, is very sparse sequence. His Brown, following similar ideas, got other polynomial two variables representing infinitely often prime numbers, etc., etc. Many of these things, and but the theory of prime numbers is very serious in my opinion. It uses machinery, but also entertaining. There are open problems which in my opinion, are hopeless to prove. One of these is for example, questioned by Erdős. So I recommend young people to get started and look for it. Gaps between primes can be arbitrarily large, as we know, and also can be bounded by absolute constant. We also know recent results of Zhang and Maynard. But if you take things in two dimension, like on a plane, and to consider so-called Gaussian primes, so that means these black dots in the picture, you have many more directions to maneuver, and you can ask, can you walk to infinity stepping only on Gaussian primes? Of course, with limited lengths in each step. So this is open question, just for your curiosity, which is, in my opinion, hopeless to touch by current technology. Making mathematics, come back a little bit to this, and learning mathematics offers intellectual joy. But one should really distinguish studying and learning mathematics from doing mathematics research. I recall problems that we were asked to solve during mathematical Olympiads, and retrospectively today when I look back, I said, how could we young people solve such hard problems? It's next to impossible. What happened? So psychology aspect matters, because you see, when you are doing tests on contests, you have a certain advantage. You know that the problem is solvable within 3 hours by a clever student in high school. When you do research, and challenge is enormous. You never have a guarantee that the technology available today is good enough to solve the problem. So it's different challenges, and if you succeed to do something like solving old problem, open problem, this is, you may think that in your life, mission accomplished. Something like that. Anything, more comments about that maybe during the conversation questions. So that's all what I would like to say about presentation. Thank you.
Thank you very much, Professor Iwaniec. Please take a seat here on the stage. The question and answer section is also about to begin. May I also invite Professor Faltings and Professor Yang to join the discussion.
Thank you both for telling us a bit about the quest for mathematical beauty and truth. Any questions from the audience, especially young people? I will start with one. I mean, we all know what mathematical statements are true. We all know what mathematical statements that are true are hard to prove. But what about the criterion for what mathematical statements or theorems are interesting? Not all hard statements are interesting.
Well, it's a little bit like on the playground. They have to be doable, but not trivial. So like if you climb up, it should be interesting, but it shouldn't be too difficult.
Yeah, I would say too that it's, you have to be some balance. I mean, easy problem is not interesting because you just answer a few seconds, but impossible problem is boring because yeah.
But that's only on the difficulty scale. Are there problems which fit on the difficulty scale and yet are not interesting?
Yeah, definitely. Definitely. Well, I mean, well, you could just sort of ask arbitrary questions. So usually it's interesting because you can do something with the answer.
And also, I think I would add to it that interesting because it fits to greatest, deepest structures somewhere. You know, yeah.
Now, I have a written question here, I think addressed to both of you. It says, mathematicians often work on their own and spend a lot of time in their own work. How would you strike a balance between your work, presumably solitary, and then balance that against your life, your family, and your social life?
Well, one is one thing and the other thing is the other. I mean, well, if you ever, usually you can't work on a mathematical problem all the time, because the usual thing, I mean, most of the time you are stuck, and sort of you work for some time and you are still stuck, and then you should do something else, like talking to your family, or vacuuming your apartment, or doing administration.
Well, I like working together with many people. If you succeed, you get very quickly, you know, satisfaction. But I think the tendency in modern mathematics is to work together in teams in great groups. But if you compare historically with how great mathematicians were working just in solitary conditions, I mean, it's so different than in other. I mean, if you consider mathematics like art, it also differs from other parts of art, like paintings. I don't recall joint painter or musical compositions, but in science, I think it's very common now. Not only in laboratories, in experimental work, but also in pure thinking. It's also much more common today to work in teams. Also, institutes are created to work in teams. Yeah.
Thank you.
I was previously a math major, and I find out that after going 4 years in pure math, I have developed a habit being a very slow reader. Because if I cannot understand one line, I can't go to the next line. I don't know whether you have that kind of experience.
Well, usually if I read a paper, I look at the statement and try whether I can prove it myself. And then I usually realize what's easy and what's difficult in the proof, and then I understand better why the guy does this or that. So maybe I don't know whether this helps you, but this is my strategy.
One other part of that question, I think, was what to do if you are lost a little bit in reading. I think one could read mathematics in successive approximations. You know, sometimes I have students in the class who are very, very ambitious. They would like to learn hard part, but they are not prepared yet for it. I don't discourage them. I want them to be in the class and say, if you understand 10%, that's a great success. That's something. I mean, you cannot just lower the level of presentation because of few younger, people in the class. And that's my way of learning. Also, when I study myself, some people's work I do by successive approximation. I don't read from A to Z. I just look where is the beautiful things first, can I capture that? And like Gerd said also, some of the lemmas, technical things, I don't even check. I prefer to prove them myself. But of course, the main line that leads to the final result is due to the author. And so this is my first approximation to understand the paper. Then, of course, sometimes you have obligation when you are referring a paper for a journal to declare that the paper is correct in every aspect, including details that you didn't read. Then it's really hard labor. Yeah. Yeah.
If I may broadly categorize those who have a PhD degree in mathematics as mathematician, then there are more and more mathematicians in recent years. Instead of working alone, solving difficult questions, rather end up working for the finance sector. What do you think about this trend?
Okay, I lost few students for mathematical, finances. Went to Wall Street, and smart people go there because they don't really see financial future in mathematics, and it's a pity because I don't think mathematicians should be driven by economical, prosperity. You should first of all love the subject. I would not recommend anybody to go into pure mathematics, like number theories, just because you can get a job. I mean, job is of course part of our decision-making, where to go and how to behave, etc. But it's not really an aspect that one should really consider as a priority. Maybe even completely disregard that. Yeah, when you do mathematics. Yeah.
So I have no moral reservations if one of my students goes into the financial industry. It's not like going to a house of ill fame or whatever. I mean, it's different well, I guess the financial industry, whether I approve or not what they are doing, it doesn't matter, it just will develop. And, well, okay, I mean, if it gives jobs to mathematicians, the better.
I think we have time for a few more questions. Yes, please.
So I was wondering, do you ever find inspiration for your work outside of mathematics, maybe in art or nature or music? And if so, could you give me an example?
Well, well, the only thing maybe at a film you see that the character overcomes the difficulty and wins at the end. So you can watch Harry Potter or whatever. But for arts, I think I'm not so much versed in arts. But maybe Henryk.
Well, I have a roundabout answer to the question. I do find inspiration by doing other things, like a hobby, listening to music, playing a little bit, recently also a little bit of photography, but not directly to get inspiration from mathematics. It's just to be relaxed, to get out of mathematics for a while in order to come back with new, fresh hopes. Yeah.
Thank you.
Could I phrase that question in a slightly different way? I mean, a few generations ago, mathematicians would find inspiration from nature. I mean, you go back to the time of Newton. And even these days, some mathematicians perhaps find inspiration from things like path integrals, which to you are undefined.
Well, I'm not sure whether so many mathematicians found inspiration from nature. I mean, after all, Newton was a physicist, so this is okay for him to find inspiration by nature. And, well, in physics, I mean, it's sometimes, I mean, the procedure is to look what physics. I mean, it's like if you have a statement, you try to prove it yourself, and so similar. If the physics people claim something, you try to prove it yourself, and sometimes it's successful. So in this sense, it's inspiration. But I would say, I mean, as a mathematician, you get inspiration from other people sometimes. Yeah.
Yeah, I can't really add anything to what Gerd said, but again, I would say that inspiration can be just affected by seeing the beauty, the harmony of the world outside nature, and okay, let me just a little bit change the subject. I would say that beauty and harmony is a confirmation that I mean, in your arguments, mathematical arguments, is a confirmation that you're on good track. You know, usually when you start doing something by brute force, incomprehensible even for yourself, it's better to stop and and open the fridge and take a beer. Yeah. Yeah.
I think we have time for perhaps one more question. Do I see any hands? Okay, last question.
Okay, wait. Hello, I'm a PhD student from the mathematics department, and my question is, when I search on some website, I found some mathematicians always work alone, but some other mathematicians work with strong groups, and so my question is, what's the disadvantage and advantage of these two kinds of work style?
Well, if you work alone, then you don't have to wait. You don't have to explain things to somebody else. And if you work with somebody else, you can always think that he will do the work for you.
Other thing I would say is that if you work alone, you are not ashamed of wrong ideas. You never tell anybody. But if you work together for decades, as I do, you get rid of these hesitations, and you do sometimes share wrong things. And it's equally entertaining and nice. You just become mathematically married, in a way. You've got your mathematical spouse.
Well, thank you both for a most interesting, delightful conversation about different ways of doing mathematics. And then I think we need to move on. Thank you again very much.